We hope to build upon the results from our previous ACE experiments, and our next step, and it's something we're currently building, is going to apply electric fields. Now, people have studied electric fields and how they manipulate colloids for decades. For example, you can control the spacing between two different colloids, as well as potentially manipulate their crystallinity, whether you want to form crystals or disperse them on demand. So by tuning the voltage, tuning, say, the AC frequency, you can manipulate the crystallinity, manipulate their agglomeration, and that's the next phase that we want to do. Now, recall that we're manipulating both microparticles and nanoparticles simultaneously, so we're intrigued to determine how electric fields will manipulate not just the microparticles, but the nanoparticles within them as well. So this is an underexplored area, and we're currently developing a platform that will go on the International Space Station to help further these discoveries. We hope to later incorporate quantum dots within our nanoparticle haloene samples. And that, with respect to solar panels, is that we hope to incorporate those quantum dots and investigate those specific arrangements and how they can enhance the solar panel efficiencies. With colloid manipulation, when you apply an external field, whether that field is gravitational effects, electric fields, temperature, magnetic fields, with all of these manipulation techniques, you can, in theory, manipulate not only the crystallinity of these colloids, but also the spacing between them. And if you can dynamically manipulate these particles in their spacing, you can control, for example, optical properties, whether they manipulate light in a certain direction or they're selected to a certain wavelength of light. You can manipulate their mechanical properties and also their thermal properties. Now you have a dynamically tunable material that could be used for a variety of applications. There's a lot of research with respect to colloid science and soft matter where you can manipulate particles and agglomerate particles, and that's fine. The next big thing is, sure, you can manipulate things at that small little area, but now let's make something that's several square inches, something several square centimeters, or even larger, not just in 2D space, but can you make it millimeters thick as well? Microgravity might potentially enable very large crystalline growth. And if you can still manipulate at this scale in terms of using temperature effects or electric fields, you could potentially have larger 3D crystals that are possible that can be created in a microgravity environment that would be very challenging to create on Earth. Large 3D crystals really just enables their integration with materials. So whether it be maybe a special coating on a car, or maybe it is a special crystal that is used within a processor on a computer, or maybe you want to have efficient heat transfer. So larger crystals will help enable either optical manipulation, electrical manipulation, thermal manipulation into, say, handheld and macro scale devices. So these discoveries or these applications are only possible when your 3D crystals can become the size of the application that you envision. If you have a glass 1 micrometer particle on Earth, you can only study that for about a few seconds before it sediments out and reaches the bottom of your microfluidic vessel. On the space station, they can be suspended for extended periods of time. So we're talking weeks, months, longer. So you can make some really astute and very accurate measurements of these particle interactions, despite them being relatively large. Even though they're still micrometer in size, they're not going to settle out anymore. So with respect to the studies on the space station, not only can you study them, but with the confocal microscopy, you can get that three-dimensional positioning of the particles and get three-dimensional crystallinity information instead of just a 2D planar sheet and getting that information. Now you have a 3D crystal that gives you more in-depth results with respect to the experiments. And even though we're disappointed knowing that the LMM is coming down, which has provided a lot of significant research, but we're also looking forward to what's coming up next. Because one of the most valuable things about the LMM is it's not just a microscope, right? It doesn't just visualize particles, which is important. You need to do that in order to get good science. But having the ability to apply temperatures, and then in the future, maybe apply optical manipulation with optical tweezers, maybe apply electric fields, maybe apply magnetic fields. So having these external stimuli simultaneous with just viewing it and also remotely controlling this and manipulating this, that's where the real value from LMM comes from. And that's where the significant science, in my opinion, can come from, is actually not just looking at it, because a picture can only do so much. Having something in a static fluid environment, you can only do so much. But with these manipulation schemes, that's where you can get some significant science and significant value.